Não precisa ligar, ele falou.
Ah, tá bom. Obrigada. Hoje a professora Beatriz.
Bom, acho que pouca gente não conhece a Cristina, né? Ela fez doutorado aqui no IAG exatamente na mesma época que o Jorge Melendes, o Bruno Castilho e o Ricardo Schiavon. Acho que está até na mesma sala, né? Acho que você dividiu a sala, não sei. E se formou aqui no doutorado, mas ela fez um sanduíche na Itália, né? Depois disso, ela foi para o Rio de Janeiro, trabalhou com o Nicolassi, né? E depois foi para Nova York. Por um ano nesses dois, daí conseguiu um emprego na Itália com a Francesca Matteucci, com quem ela já tinha trabalhado, né? A seguir ela foi para a Suíça e trabalhou em Geneve com o André Meder e o Georges Menet, e daí obteve um emprego na Alemanha. Então, ela está na Alemanha já faz 20 anos? 14 anos. Mas a gente continuou colaborando todo esse tempo. Eu lembro que foi a minha aluna num curso de populações estelares, no qual estava também o Hélio Rocha Pinto, né? Então, tudo coisas que já são históricas, né? Sim, a Cristina colabora com várias pessoas daqui, né? A Silvia e comigo principalmente, né? Então, a Cristina pode começar.
Obrigada. Então, primeiro, obrigado por me deixarem falar aqui para vocês hoje, nessa Semana da Pátria, né? E é sempre uma honra falar aqui, e principalmente que esse auditório tem o nome do Paulo Benevides, que era um grande amigo meu também, que eu gostava muito dele. Então, vamos esperar que me inspire. It's in English, no?
Yes.
Yeah, sorry. So, oops. So today I gave this talk the other day on the Astronomia do Meio-Dia. It was more on the solar vicinity, on the very old stars here, and about galactic archaeology. Today we are diving into the bulge of the Milky Way. And to start this, I put here an image of the Meerkat. It's a radial image from the very center of the galaxy, next to the black hole that we know we have in our galaxy. And here. And this is a very beautiful image showing that showing the gas, essentially inside the galaxy, where you see, for example, very clear some remnants of type 2 supernova. I did something wrong, probably. No? Okay. And they made this image very nice, and also there is one insert with an image from James Webb. And the idea is just this image to tell you that we are in such an amazing time for all this technological, science and instruments, satellites, but also telescopes. And a lot of what I'm going to say is not going to talk about the gas, going to talk about the stars. But it's just to bring this into the idea that we are really in a moment that's special. I am here in Brazil thanks to Beatriz, and we have also support from FAPESP. And of course, we do not do any work alone. So I have a very nice group of collaborators, especially in the topic of bulge here. So the bulge that I'm going to talk to you and what I'm going to show you, it's depending on the fact that we have Gaia. Let me just do something here. So because we are in this Gaia era, a lot of things I can show you we can do only now for the bulge. And that's what I wanted the outcome from this talk to be. And here what you see, Gaia gives you the colors of the stars, the position, and the transition velocity. And once you have this data, you can combine this with, in our case, Star Horse spectrophotometric code to transform this data into distance. So to obtain the distance, of course, you need the extinction. And so this, what you're seeing, is a map of our sources that we have run for Gaia-DR3. The last EDR3 or DR3, the last data release of Gaia has shown data from 34 months of data. And the next one, the DR4, will be 60 months of data. So everything we are using now has only 34 months of data from Gaia, and it's already revolutionary, right? So we have to, another thing that's interesting, not only Gaia, but there has been a lot of development in infrared. And last year, you have this paper by Roberto Saito et al. From the VVV and VVVX collaboration, where they are mapping in infrared all this low latitude region. And that was made in the Vista telescope. And that camera, the VIRCAM, has been now put out and is making space for installing Foremost. Foremost is a spectrograph with more than 2,000 fibers that will now do the spectroscopy, and of which I was the project scientist by the time we were in competition still to make this project happen. And it's very nice because now in July we have the first image of installing the instruments in the Vista telescope, and everything is going very well. And if I have time, I'll show you after. So this shows you the power of the VVX camera. In this paper by Roberto, he showed, for example, this image of a Carina Nebula on the disk, and you see the quality of this. So really technology all the way into all what we do. Here, because they have this, they can obtain amazing CMDs. This has been shown already, for example, in 2019. For each of these fields, you can get a CMD of the bulge area. And with that, you can obtain a color magnetic diagram. For that, you can obtain also an idea of the age of the stellar populations in different parts of the galaxy. So along these years, there have been some reviews about what we understand about the bulge of our galaxy. One of them was written by Beatriz Barbuí. But all these, most of them happened before Gaia, and you know, a lot is happening, and a lot is happening thanks to Gaia, but also to VVV and to other things like APOGEE. It's also a spectroscopic survey that plays a lot of role in the bulge. So why do we want to study the bulge? There are many reasons, but here I would like to point to something. We know other galaxies have bulges, but how do we relate what we see inside our galaxy, looking from inside, to what we see to other galaxies, where you see the bulge and a projection of the bulge? So it has been very difficult to have a model of the formation of the bulge. Different models predict different age distributions, and ages is one of the most difficult things to obtain. So that is an open problem. In the bulge, we expect that we find the oldest stars in our galaxy. Now we know there are some older stars also here in the vicinity, solar vicinity, but they could have come from the bulge as well. And there is a certain, you can put the old bulge of our galaxy in relation to what we are seeing in high redshift, because in high redshift we are seeing the first generations of stars, especially going to JWST, where we have found, people have found really old bulges already formed, very high redshift. So maybe there is a relation to some also weird objects we see inside our bulge that are globular cluster-like, but not really, where they have objects like Terzan 5 and Liller 1, which seems to have a spread also in age. So, and it's also debated a lot, what is the fraction of young stars in this old bulge? So when you take a CMD, the population looks very much old. But when you go for some field stars for which you could get age, which are the lensing, gravitational lensed stars, that you can put them in the CMD in the mean sequence turnoff and get some age, the kind of age we discussed in the other talk I gave. But then you seem to have a contradiction that the two techniques give different ranges of ages. So the CMDs tend to give very old ages for this region, while this data from BNSB, for example, gives you a large spread in age. But what I would like really to study is like, one thing that is being debated a lot is, can our galactic bulge, here defined as a 10-degree square there in the bulge, can this be explained only by a secular formation? So a disk that forms a bar, and that's what we are seeing. So there is not a real old spheroidal bulge as also postulated by some models. And now that people are finding this pressure-supported component, which I'm going to show you, there's also some claims that actually this is not the old bulge. This is still related to the bar, and this could be a kind of a splash of the old disk bar that was there inside when Gaia Enceladus hit us. So that's how we are. It's a mess, the study of the bulge. And I think we can learn a lot, both by going to the bulge like I'm going to do now, but also by learning, studying in detail the very metal-rich stars at the solar vicinity, for which we have age and chemistry, so which I'm not going to cover today. We are in the bulge. Okay, so thanks to VVV, another way to trace the bulge in terms of age, that's very powerful, is globular clusters. And now with Gaia, you can also compute the orbits of these globular clusters, and you can also see that they really are part of the bulge. And this census of globular clusters in the bulge has also increased now the number of globular clusters thanks to VVV, obviously, right? So in this review by Bika et al., you have a lot of other globular clusters that came into play. And this is an LB of more or less 10 degrees, minus 10, 10 here, and you see more or less where the bulge bar would be. So here in the southern part of the bulge, you have less extinction, and that another survey that very recently has started and has shown results is called the Blanco. It's using the Blanco DCAM bulge survey. Is this footprint here in the south, and there is only photometry, but is also giving interesting results. These are their CMD. This gives interesting results because they have a color. One of the colors that is dependent on metallicity. Here you see the red clump for 3 different fields, for 2 different photometric colors of the BDBS, and you compare with VVV, for example. So with that, I'm saying there's a lot of photometric information also available, okay? But there is no spectra here. Now, we want to do more. We wanted to cover this region with foremost, which is this instrument that goes in the VISTA telescope that has many fibers. It's in the optical, so we can only do the low extinction windows. And we have broken, I am the responsible, together with Ivan Minshev, to cover this part of the galaxy, bulge and disk of the galaxy. And this is the kind of area we are going to cover with foremost. Okay, and here we're going to have another field, which is very much sitting in the BDBS, which is called bulge deep, which is the one that Anna Queiroz is responsible for. She's taking lead in that survey. So foremost, I am doing solution survey, even though I'm interested in chemistry. But as I'm going to show you, here are the different elements that are going to be in our wavelength range. The low resolution of foremost has a very large wavelength range, and that brings a lot of elements. And we are confident that also in this Gaia time, we can analyze this spectrum with more information that comes from Gaia, so that we can get also good chemistry for this data set. And we have been working a lot on machine learning approach to show that this is possible in intermediate low resolution spectrum. So definitively our survey is not only a radio velocity survey, it will be also a chemical survey. Okay, but before we have all that, this is what we have now. That map I show you from Star Horse in the sky, you can transform it in 3D. So here you are seeing 40 kiloparsec to 40 kiloparsec, the distance of Star Horse in X and Y, so the galaxy seen from above, or in Z and X, the galaxy from the side. And that's amazing that we have this distance, so that it's almost like we are seeing our galaxy from outside. All the data that we have made to compute this, so distance, extinction, and some stellar parameters, they are available to the public. We make releases that you can use, and it's very much used. For example, this 2022 paper has something like 200 citations. But we want to go further here. We don't want to be only photometry. So in that box of 30 million objects for which we managed to run Star Horse. We have here the spectroscopic surveys are now seen in X and Y, and we have a box of around 30,000 stars which cover the bulge area, and most of them are coming from APOGEE. And so here's when we combine the Gaia, the photometry, and the spectroscopy, and this is also a data set that we have produced 11 million targets for which we have computed distance using spectroscopic information, and from these 2.5 million targets have also ages, but only those around us in 1 kiloparsec or 2, for which they're falling the main sequence turn off, and therefore we can give isochron aids that are more confident than going to the giant branch. We have used these data sets for other papers of some are linking to Brazilians. Guilherme using our run for Segue to trace the Sagittarius, and also this last paper on the age of the disk, the thin disk. Now, our distances are precise, especially when combined with APOGEE, and we show this here, showing this very inner galaxy. So it's the inner 4 kiloparsecs of the galaxy, where we see this pattern in radial velocity, which is what we expect when you have the bar. And these results were very important because it's the first time we could show this from both sides. And after this was also seen by other results, and this comes often in simulations as well. So this is yet another constraint. And this, for here, I'm just showing that our distances really are really good. Okay, so you have had here at IAG the talk by Anna where she showed all the work she did in the bulge, and I'm gonna take it from there and bring you to what we are doing today and why we need. So essentially, what Anna has shown you is that she has taken, this was her PhD thesis, part of her PhD thesis with me in Potsdam. She has taken this APOGEE Gaia information, so run of Star Horse, which she helped to develop it. And we throw our sample, what we call RPM sample, a sample that we are sure that are very much inner galaxy. We throw in a diagram. We could compute orbits for this sample, and we could throw our stars in a diagram of Zmax eccentricity. Why is this important? Zmax is the maximum height in the orbit of a star, no? And eccentricity is the eccentricity. And you can, it's a high resolution, these are high resolution data. This is APOGEE, and so you have a lot of chemical information. So one of them is metallicity. And immediately you see, and she has shown here, these stars, they have more metal rich, more confined to the mid-plane of the galaxy. As you go up, you have lower metallicity. What is important is that it was one of the first time, if not the first time, we could transform the normal analysis of bulge samples that usually was in L and B and seeing how the properties vary. We could now move on and do this analysis in orbital space. And that is very important. Why is it important? Because in the middle, there in the bulge, in this inner 4 kiloparsec, there is a mixture of several stellar populations. There is an inner disk, thin and thick. There is the bar. There is maybe this spheroidal bulge that we're looking for, and it's very hard to see because you have everybody else in front of that. And that's exactly what we want to see and constrain. So in the work of Anna, she showed the existence of all these coexisting populations there, and also the fact that is in this area that we have a larger reservoir of very supermetal rich stars, stars that have a peak of metallicity above 0.2 solar, almost 0.3 solar index. That means 3 times solar, and that's where they reside. Okay, so we have to move on from this. What was interesting is that also showed that in this area here, for that sample of APOGEE, the stars with larger eccentricity and not so low Zmax, they had resemblance, their kinematic resemble a spheroidal component, okay? But as you see, most of our data is concentrated to the lower part. So we show that this looked like we had the spheroidal. And interesting, the bulge globular clusters that Beatriz is studying also with Stefano, they sit in the same place, okay? So that is showing an idea that exists a population in the middle of all this mass that is in the bulge. But here we had a low statistic. So we had very few stars that were here because we were looking with APOGEE from inside. And so we needed to better sample where the spheroidal component of the galaxy is Here down is dominated by the bar. Here is dominated by the thin disk. Here you have a lot of thick disk in the middle of balls here. And here is where we think the spheroidal bulge will dominate. And we needed to find a solution to see more of the stars there. So then it came Gaia DR3. So the difference between EDR3 and DR3 is that EDR3, we got all the astrometric information for Gaia. But then at DR3, we got also the XP spectra and the RVS spectra. Okay? So with that, we could do two things. Using the XP for millions of targets. So here we took, in this work, 200 million targets. We could now use the runs of star horse that Anna had done in using Gaia plus spectroscopic surveys to inform a machine learning version of star horse. And this machine learning works amazingly well. Essentially, it learns from star horse, from the runs of star horse normal, and use the XP to break degeneracies. This XP that come from Gaia DR3 as coefficients sounds very abstract, but these coefficients are dependent on temperature and metallicity, and so they break degeneracies, which is one of the difficulties that you have, because you have a degeneracy between metallicity and color, right? So this is what we try in this paper, how to use this XP, and we have done, are all the products that we have been doing with Star Horse. To do this, we did this machine learning method that's called gradient boosted random forest regressor. That's a small way to call it, is XGBoost, trained on Star Horse run, but also using other samples to complement the training sample, which is the brain of all this thing. So when we do this, for example, we find that now with millions of targets that indeed we are getting from XGBoost an idea of metallicity. Imagine I don't have any spectra. So we have an idea of metallicity, and if we project in X and Y, we see that these super-metal-rich stars, they really are where they should be. So they are populated the inner parts of the galaxy, right? So one thing I want to say is that what we saw is also the fact that it took us weeks to run the whole Gaia Star Horse thing, while here, in 2 days, we did these 200 million objects. So that is really a gain in this machine learning job, but you need a training sample, so you're always going to keep needing some classical Bayesian inference thing, which is what we use, like the Star Horse is. Okay, so Anna has shown that the very inner part of the galaxy, if you plot oxygen over iron versus iron, you have this dichotomy here. And that you see this dichotomy not only in people had the idea that you would see it not in the bar stars. The bar stars will always be metal rich and low alpha, and she showed this is not the case. Other samples that have appeared in the literature cover more metal poor part. Here you see I'm minus 1.5 to solar, or above solar, 0.5. And it was missing a sample that takes this intermediate thing between the apogee sample and a bit more metal poor. And we figured out that actually we could use the RVS. Gaia DR3 didn't bring only the XP spectra, but got also the RVS spectra, which are really spectra of a very short wavelength range, but with a resolution okay, something like 10,000 in resolution. So this, why is CNN? Because here too, if I go to the spectra of the Gaia-RVS, most of them are very low signal to noise. And so I don't manage to extract stellar parameters that are precise enough for most of the sample. I can do only for the high signal to noise sample. So we use a machine learning to make this RVS data set more powerful and manage to analyze this. And this is, I don't have time to explain, but it's in this paper of Guillaume et al. 2024. Okay, so now we are entering the bulge with two samples. We're going to use the RPM sample of Anna, so the sample that she presented in a talk here before with apogee that I'm showing in green, and this RVS sample. Most of the RVS sample is sitting here in the solar vicinity, but now we're going to manage to see the ones that reach the bulge. Who will be the ones that reach the bulge? The ones that are in the giant branch, the brightest ones. There are a few. Most of the science I showed before in the other talk was here using this RVS at the solar vicinity. But now you're going to see these stars that get to the bulge with the RVS. And what's the advantage? We're going to see a bit lower metallicity. Okay. So And this is that was the extinction map computed by our extinction map. And you see that, of course, the RVS is optical. More optical is going to be sitting where there is no extinction or little extinction. Okay. The nice thing is that the CNN parameters, stellar parameters that we put to use this sample, even though it's a low resolution sample, is amazing, goes amazing well with APOGEE, which is a 20,000 resolution sample. So this gives us confidence that we are entering into this game with good stellar parameters. Why is this important? Well, this is the key, because if you have bad stellar parameters, forget about everything else. Our distance, our extinction, everything will be compromised with that. And why you did good distance? Because you wanted to compute orbits. And if you don't have good distance, your orbit is also going to be wrong. So this step is very important. You see, the RVS is 11,000 resolution, and the APOGEE is 20,000. The APOGEE is in the H band, and the RVS is optical. Okay, so now we're going to enter into the bulge, and this is the paper I wanted to show you. This is what we're going to call bulge sample. So everything that has, now we don't need to anymore choose a box in X and Y or in R. We can do apocentric distance. You see, we have the orbit. We can choose all the stars that stay confined to 5 kiloparsec. Apocentric means the farther radius in this orbit that the star reaches. So we have what we can, the normal way to define it in the past was like you take the current radius below a certain value. So below 5 here, for example, for the RVS. But now we can define it, because we have the orbits, we can define apocentric. And this is the kind of sample we're going to be working, which we're going to be called bulge. You see immediately the green is the APOGEE, and this black is the RVS, and they are very complementary to each other. Here in the back is the sun. Most of the stars of the RVS, as I said, are here next to us, but we have a lot of stars that reach the bulge. And that was the very good thing. And we only have because we have analyzed this with CNN, and therefore we are using stars with down to signal noise 20, for which you have good parameters. Okay, so this is our sample in Z, height from the midplane, up and down, and in radius. So it's not an enormous sample, but it's a good sample. Of course, as I said, we're going to be in the giant branch, because this will be the brightest stars that reach there. Of course, I'm not going to get age, because I can get age only for the stars that are in the mean sequence turn-off, which are the other papers we discussed the other day. But now, when we look to the bulge, now here is latitude and longitude. This 10 degrees, this 5 degrees, 10 degrees, 20 degrees in wide. You see the metallicity distributions at different positions. And you see there's a mess. So the metallicity distribution around the bulge, if you look in L and B, changed radically from one position to the other. We knew that already, but now you can know this with more statistics. And this is a hint that there is a mix of stellar populations in this region, okay? If I do a zoom in the inner 5 degrees, you see here what I'm meaning. These are the different metallicity distribution. Here are sitting the bulge globular clusters that Beatrice has been studying. And this magenta thing is where it sits the Bainsby stars in terms of metallicity. So the Bainsby stars, the 90 or whatever stars he used that have lensing, they are sampling all this metallicity range. And in this metallicity range, I have a mix of populations for sure. Okay, but we are not going to be here. So the first thing we're going to, so that's what I'm saying. So here's the globular clusters that are in this paper. And here the Bainsby sample of stars. Okay, first thing we're going to do, we're going to take out from our sample everybody that show bar orbits. And for that, we're going to have to do we would need to do a probabilistic approach. There is a way to do it, but I'm going to jump that. So let's suppose I do it. And now I have, for the stars that have high probability in being bar-shaped orbits, they divided in several families. So here are all of them. And here is the typical orbit they have, depending on some frequency. There are different kinds of stars in different kinds of bar orbits. And for each of them, I have alpha iron. And I can show that in whatever family I go, I have high alpha and low alpha, high alpha and low alpha. So it's not true that the stars in the bar are low alpha stars. And why is this not surprising? The bar of a galaxy is not a stellar population. It's a structure which is made after from whatever stellar population was there. So it should be a mix of stellar populations. So up to here, everything should be okay. And the expectation, simplistic, that the bar should have only metal-rich and low alpha is not confirmed here. Okay, but we're doing this. Why are we taking the bar from the front? Because now we are left with something that we use another parameter here, which is the mean angular momentum in the z direction. So essentially, we find that we are going to define subsamples based on kinematics, that we have orbits and we have good distance because we have all the Gaia parameters. And that made that we could have a sample which is essentially non-rotating in that place there in the inner galaxy. And here I'm showing the orbits for you. It's essentially a spheroidal that has some dependence with metallicity. Here you see different beams of metallicity, metal poor to metal rich, right? Most of this component is sitting here between -0.5 and -1. So if we do a step further and compare the different stellar populations that were there, if I do here the metallicity distribution here, we see that in blue here, you have the stars that are in bar-shaped orbits. Only for them, indeed, you have a lot of stars at very high metallicity. But they have also important contribution of metal-poor stars. The magenta are the stars that are not in bar orbits, but still have a V5, have a rotation. They are thick disk stars. Thick disk extends to the part of the galaxy where I am. I can take them out by using one of these kinematical parameters. And what is left is this black line here, which is essentially the spheroidal bulge. Notice that the spheroidal bulge peak of the MDF here is at -0.7, while the peak of the thick disk there, not here, there, is -0.45, which is very similar to the peak of the thick disk here. You see, so this gives confidence that we are really seeing kinematically one population that is a node spheroidal and one population that is the thick disk, and on the top of that, a bar that's mixed in all this population, okay? So, I'll call this inner thick disk, bar structure, spheroidal bulge. The dotted line is a very interesting. These are X4 orbits. These are orbits that do not follow the bar, but are there only because there is a bar, and they are there because they capture things if before the bar formation there was a structure there that was spheroidal. This is amazing. There's just a small amount of why is amazing? Because the metallicity distribution of this, which is in the dotted lines, is very simple to the spheroidal, is very similar to the spheroidal bulge, giving yet one more suggestion that this spheroidal bulge really was there before the bar formed. Everything I'm saying is very controversial, by the way. Now, I would like to have the ages for each of these populations show they are really different populations. That's not possible. There is no age. So we think those are younger, and I will jump this part. But we think also here we know the age of the thick disk at the solar vicinity, and so we think this could be indicative of the age of the thick disk there also, and that is around 11 gigayear. And these are the papers about we knowing it at the solar vicinity. And here we expect it to be 13 gigayears, very old, the oldest population. And that happens to be exactly the same age that the group of Beatrice is finding for the globular clusters in the bulge. So that's the link we have with age. Okay, now I'm going to project for you these different populations that I found in the famous alpha Verarum versus Aron plot, which is this diagnostic that you understand because it shows you some time scale. And here you see the bar. A lot of the bar stars are indeed at low alpha and high metallicity, but there is a non-negligible contribution of high alphas, as we saw before. The thick disk show this behavior, show a behavior of alpha Verarum falling with iron, while what I'm suggesting is the spheroidal bulge keeps a bit flat here up at very high alpha, has some contribution of this, and that's expected because if there was any kind of splashing of the orbits for any reason, there would be orbits that are in the bar that end up hit dynamically, and they could be entering this spheroidal bulge here. Okay, if I go now to the ones that are in this sum but are not confined to 5 R-APO5, but they can just passing in the bulge, but they are actually passing the halo, I find the debris. And this you see, these debris are not exactly in the same alpha variron than what I'm calling bulge. They are displaced to low metallicity, and they are a bit lower, exactly like we expect to be the case of Gaia-Enceladus and other debris in our galaxy. So it's really nice. So this is really the first time we do this kind of analysis in the inner kiloparsecs of the galaxy. And this paper is in the AstroPH for more than a month and a half, and we didn't get any referee yet report. Okay, so now I hope I try to convince you that we have an old bulge there in the middle. I don't know, I didn't convince you this old, but we think it's old because it's sitting exactly where the globular cluster is, and that's what I'm going to show you. And now we could go, and if we know more where and how to select the bulge stars and not being contaminated by bars or thick disk, then maybe we could finally prove if this component has a different chemistry than the rest of the components. For that, I need a high resolution spectroscopy and a lot of work. So the one thing I want to show you is that I told you that the bar trap thing, so the bar mixed stellar population, and here we published recently an example of that. So here is the bar, and we found this star that has an orbit that put it in the bar, is doing something like a peanut inside the galaxy. And if we look at the chemistry of these stars, here these black points are several alpha variron and several chemical things for a box of stars that are there, the RPM sample of Anna, I'm showing here. And we see this star, we see this star here that we found is doing a bar orbit, but has some specific chemistry that is offset from the main component, the main chemistry of that region. And interesting, this offset follows what you expect for a second generation globular cluster star, stripped from the globular cluster, because these are the kind of, these blue arrows, let me just say this very quickly, these blue arrows indicate what you would expect if this is a second generation globular cluster star that was lost into the bar. And we also give an idea when it was lost and from where it was lost. And we think it's from the Tarzan 5 building block of the Milky Way, because it is sitting here very similar to the most metal poor part of Tarzan 5. This is really like going to the details of chemistry here. Essentially, very recently, also in a paper by Aurelia, she showed that there is a lot of similarity between bulge field stars and Tarzan 5, suggesting that these kind of objects contribute to the building up the bulge. But we didn't have age again. We thought we would have age, which would have been amazing. We have seismology for these stars, but the seismology was bad enough not to give us an age, so it was very sad. Okay, another way to go for high resolution is like this. We take the RPM sample of Anna, and we select here now the most metal poor stars, and we make a selection such that is high eccentricity, has a low Zmax, so it's confined, and so on, very similar to what we are finding in the big sample. And we see where they are here next to the globular clusters that Beatriz is studying. And we now, for those stars, get a very high resolution data. First, let's see them here. Zmax eccentricity, as I showed before. Behind here is our RPM sample. These are the stars of Hazera et al., the paper of Beatriz, where we select here. And that's where they sit. So they sit more or less where we think is the bulge. And these blue stars here are the bulges are the bulge globular clusters. Interesting. If I put here in the work of Ortolani, but also Stefano, 2024 and 2023, if I put here the metallicity versus age, I see the non-in situ globular cluster, but the in situ globular clusters here, these are Stefano's globular cluster. I see that our bulge that I'm suggesting fits exactly here. -0.07 is the peak, and so it should also be something very old, around 13 gigayears. That's the idea, to give an age for the bulge without having the age of individual stars in the bulge. Okay? Finally, the chemistry gives you another opportunity. People have been using this diagram here to select who is ex situ, who is in situ. But the globular clusters show things are not so simple because a globular cluster can have, an in situ globular cluster can have a first generation here and a second generation here. So you mix things. And indeed, the globular cluster of Stefano and Beatriz are sitting here, in between. So it's not so simple, this kind of thing. And our 58 stars that were now measured the chemistry for these stars by a series of paper, but particularly this one, is these yellow points. You see that they span also that region, even though we think they are in situ. So there is a lot of complications that you enter to once you know the detailed chemistry of this population. And you see that this population is not sitting here in the main thick disk and thin disk populations, which are sitting in these two blobs here. So we need, and that's what I wanted to do here, we need to do a reanalysis of all the high resolution spectroscopic data and see how this fit into this scenario that I show you, where we have an inner thick disk, a bulge, and a bar. And so that's what I'm here for. This is the goal of what we are doing here. There are other results of chemistry that I'm gonna skip because it's too much. Let me just go to. Of course, we are seeing something weird. It thinks at around -0.07 when you have a sample that mix all this, but we are seeing some things that are interesting. Okay, so now we are hitting a wall because we managed to go inside the bulge, we managed to have orbits, we managed to disentangle stellar populations using kinematics, and then confirm they are really different by looking to their chemistry, because if I'm doing everything wrong, their chemistry will be all looking the same, and it's not what's happening. So that shows that the chemistry is following the kinematic. And so it's really, I'm really able to disentangle stellar population. However, we lack precision in age here at the solar vicinity when we wanted to get age for stars at the solar vicinity, but also in the bulge. And there is only one way forward for that, and this is the mission we are trying to sell to ESA, okay? And I want to briefly show you. So this mission is called HADIN, High Precision Astroseismology in Dense Fields, and is right now a candidate for M8 mission for ESA. We have gone through this for M7 from more than, I don't know how many, 100, then they select 20, then select 5, and we made all this thing. We were even selected with the 5, and from the 5 they had to drop 2, only 3 went ahead, and we were dropped. So now we are going again. So it requires a lot of patience and work. But for example, we definitively need accuracy in age determination. So we need to make one step in stellar models and solve some problems of stellar models that give you systematic. So one example, this paper will be on AstroPH tomorrow, is an example where we use the oldest stars in the Milky Way, computing by Star Horse with very good parameters, taking account of the systematics that we know are in the models here in the solar vicinity, to kind of give an idea of the age of the universe. It's a very interesting work. But this shows, and you see that we hit the problem of statistics, systematic. Now that we have statistics, we are really hit by the systematic of stellar models to be able to give good isochron aids. So why do we want a mission like this? Well, all the astroseismic missions, they had a very big PSF. And if we want to do the bulge, we need to have a very small PSF. So that's the first thing. So the PSF of HADIN here is 1.3 arcsecond. And then we need to be sure that we can give aids for red giants. Why? The red giants, we cannot give isochron ages because all the isochrons, the other things are together in the giant branch. We can only give isochron age to bodies the main sequence turn off. So for the bulge, I'm having giants, right? Because they are far away. I'm not going to see main sequence turn off unless I have ELT. Therefore, we're going to have to use astroseismology. And now there has been a lot of effort from other groups showing that the masses and the age of astroseismology give really good accuracy, not only precision, but accuracy. And for example, this is a very interesting paper where they found one eclipsing binary for which they get the mass, and that's in the thick disk, and for which they compare the mass from seismic and eclipse binary, and they are within 1.4%. So really very accurate. These are these two values here. Very accurate, which you need to know the mass better than 2% in order to have an age better than 10%. So that's what's happening now at the solar vicinity. And we think we can push this to Hading. So what will be possible with Hading? Right now, people are showing that they can get precise ages from seismology that give you masses between 1 and 2% precision. That will give you ages at 10 precision level. When you couple with chemical information, so you need spectroscopy for this to get this precision, and then get this precise age for the RGB. This is feasible nowadays. But we have this wall in front of us, and the accuracy is always sitting behind the wall. We never get accuracy, really. And this jump we are going to do with Hading. And so how are we going to do that? We're going to constrain. So by looking clusters, Hading is going to focus on clusters. And then you constrain the structures of the stars, because seismology gives you a lot of information from the inner parts of the stars, and therefore constrain stellar models for the stars that are nearby. So we're going to focus here is what we call precision sample, M67, 47 tuck, in different metallicities, you see, solar and -08. These are key cases in a key metallicity interval. Notice that this metallicity interval covers where we think the bulge is sitting, right? And then with this step here, which is a big step and is where Hading will pass most of his time observing clusters, we can pinpoint the systematics in stellar models and improved models. And then finally get accurate ages. And when we have that, we can apply this knowledge to the Baddest window and get precise and accurate age also for bulge star. That's a long run. We have written 2 papers that explain that. One is for this mission, Hading, and the other one that's a mission that's called, hopefully, Gaia near-infrared, which will be also doing Gaia now in the near-infrared, because Gaia, as you saw, for example, for the RVS, I'm not peering in the inner parts of the galaxy. So we'll finish just by saying that we just had a mission to define the main science that we're going to do. Now we had a conference in July. This is the people that are involved, mostly from, well, there's from several places. And this is our milestone. So we passed the first step proposal we sent. And now in September, we're going to know if we pass to the second phase. And then we have to prepare the second phase proposal. And again, go on into this thing. For Gaia, so you saw here the dates. Now I'll talk to the young people. 2041, okay, is Hading coming out, giving you precise ages in the bulge. And now, Gaia infrared, this is the time scale, also 2040s, but maybe 50s. That's also the idea of Gaia infrared is still being considered. It's not, you know, it's not the taking out. So that's the future. And then I wanted to finalize by saying that the breakthrough in galactic archaeology, after we have Gaia, after we have the spectroscopic surveys like foremost, will be really this age precision that will need to be better than 10%. And you say, why you need to be better than 10%? Because I show you the difference between the age of the thick disk, the spheroidal bulge, if you are convinced is there, and also when the bar formed and the age of the stars in the bar, all this happened, the action in this galaxy happened in the very beginning of the story. And so it makes difference if we can really pinpoint this difference in age. We need resolution in age, which is something we still lack. So we're gonna be able to do that in 2050. And then by then we also have other stuff here, very important. We're gonna have, for example, the ELT instruments. We're gonna have also the VLT second generation instruments, for example, HR mod. So the young people, you are in the right moment. If I was you, I was going to start doing galactic archaeology immediately. That's it. Thank you.
Thank you, Cristina. Very nice talk. Questions?
Cristina, your last slide is very interesting to me, because I think that I don't know how it is possible to disentangle an 11 giga years old from a 13 giga year old spectrum.
It's not only the spectrum. That's the point. We will now have all the information together. And we show this, for example, in this paper that will be in the AstroPH tomorrow, and that I am happy if you come to criticize. This one, so what happened is that right now we have statistics, right? So for example, this sample that we are using are, for example, stars that have very good stellar parameters that are sitting here, 700 parsec around us, for which I have Gaia spectra, okay? And I have Gaia information. For that sample, the parallax error is essentially non-existent. That translates in a distance for those stars of precision of 1%. So now when you put the stars in the CMD and you're passing the tracks of the main sequence turn off, you know exactly the position. You have a very good metallicity and you have a very good log G, because it's assisted by the parallax information and by the XP information. So all this makes that you have stellar parameters very good for these stars. And now you go and run the ages for this. Of course, where are you're gonna hit the systematics. You're gonna use one set of evolution of stellar models, right? For example, in our case, parsec. Once you do that, you see that there are a lot of stars. Now, the sample that we start with was 200,000 stars for which you can obtain age. We never had this before. 200,000 stars for which the parallax is good at 1% level. We never had this before. Now we have. Now, you select from these the oldest ones. In this case, I'm not caring about bias. I'm caring about the age of the universe. I select them, and you have 300 stars that have beautiful PDFs. You have a PDF for a probability density distribution for all parameters, and you see that there are some that you really trust. So you go and you cut, you get still 70 stars sitting here nearby for which PDF is perfect, metallicity looks perfect, everything looks perfect, and it comes out with an age of 13.5, 13.2. I have nothing that obliges me to be 13.2. It's open. I run Star Horse without a finite age for the universe. We run Star Horse leaving the star to be 20 giga-year if it wants. So it's amazing. These things are starting to work. We are really in a change of moment that is risky. It is. But it's risky because of the systematic. We are getting so precise that we are hitting the systematic. And if we don't do something about this, we're going to keep here. We never move on, you know. So that's why we are applying in some cases to really tell people, okay, even if you do extragalactic and you're worried about the Hubble constant, here it is an example where we are combining, for example, the globular clusters that I'm showing you, that's also getting amazing data, is giving me an age. And here the peaks of these stars, which is our final sample, is also giving you an idea where this H naught should be and should not be.
Okay, thank you.
Cristina, very nice talk. Let me ask you, going the same line of reasoning about aging, when you showed the other diagram where you have the distribution of the components and you have this older bulge.
The older bulge?
Yeah.
Yeah.
So this, how old it would be compared to this hint that the spheroidal bulge is 13 giga years, around 13 giga years. Can you have an insight for this already?
I don't know if I understood, but I mean.
No, I mean the, yes.
So here we have a component that is not a thick disk and is not in the bar, okay? Right. Now, this component, I don't have the age, but I know that this component in the orbital space is sitting exactly where the globular clusters of the bulge are.
Right.
For those, I have precise ages, really precise ages, because they have amazing HST color magnitude diagrams, and this is the tip of no? So I have an age that's around the 12, 13 giga years old. Now, for the thick disk, I also start having precise ages, because not there, but here, at the solar vicinity, I have different ways to estimate age. For example, in the paper of Anna Queiroz 2023, we take the thick disk out, and we have the age now in the main sequence turn off, and we get 11 giga years. Then I go for another sample with seismology with Andrea Miglio et al. 2021. We have, it's also a paper that's a lot of citations, because we have a very good sample, precise, with seismology, with Kepler. Kepler is the best seismology. So in that case, I select something chemically thick disk, again is 11 gigayear. So I am kind of, from the solar vicinity, I'm hinting, and from the work Beatrice is doing in the global cluster, I'm hinting that there is a difference between the thick disk and the spheroidal bulge. And it is hinting to me that maybe the oldest stuff is in the bulge. But then, now, I have a problem, because I have found some very old stars here, right? Same age, also very old. So why? What are them? That's why we think is now the moment to really understand this interface between the bulge and here. Notice that you cannot get this kind of data for any other galaxy. I mean, this kind of stuff only here. And it looks like some stars from the bulge end up here. And we know that because we have here in the solar vicinity stars that are very metal rich, much more metal rich than the current gas in our galaxy here. So they cannot be from here. So that's where all the discussions now going on. But if we don't move on in terms of accuracy for ages, either here or there, we're gonna stay with all these questions open.
Right. But the bar may have an important, maybe a key component for providing this mixing, right? This dynamical mixing, bringing very old systems to outside the older bulge,
so now
right?
we have two options. Maybe the bar is bringing the very old stars from the bulge here.
Exactly.
And the other option, maybe there is a very old disk, thin already, that was here, and very difficult to see because most of it was formed later. But maybe this is a very early thin disk of the Milky Way, which also got interest because at high redshift, you're getting earlier and earlier thin disks there, right?
Right.
So it's this mess that we are. And the overlapping parameter space for chemistry and kinematics is huge. Right. That's why it's so difficult. So we hope that by having more idea of other chemistry, we can figure out a chemical element that can help us for that, or also combine it with age. There are some hints in the work I'm doing here with Beatrice that there are some weirdos, chemical elements, that now we don't know if it's an uncertainty in their measurements or if it's true, you see? That's why we are in this moment here.
Right, thanks.
Hello, nice talk, Cristina. Very informative, lots of things. And my question is, it's about the bulge also. So, in the Milky Way, we have a spherical old bulge. And do you have some evidence of the building up of a pseudo bulge through the material that's going inside the galaxy through the bar or the arms?
Yeah, that is the people I took out from the front. So surely big part of what is in that box of 10 degrees is the secular formation of the bulge, which we see is a peanut, right? So it's not saying it's not there. I'm saying they're contributing a lot, but we are biased to that view and we are having difficulty to see this component that maybe was there even before this, right? And so that's why there's a lot of other constraints in this paper that are for people studying buckling of bar. That's why, for example, I show the chemistry, how it depends on the different kinds of orbits. And you saw the different orbits span to different regions, so they mix different things. So there's a lot of constraints also that hopefully are going to pinpoint better the buckling bar problem as well. But all this is very difficult because simulations for that, which is another tool, is to compare to cosmological simulations. The difficulty is a lot of cosmological simulations not forming bars, or forming bars because they had resolution, low resolution. When they go high resolution, the bar disappear. A lot of simulations that form the bar do things well, but they are not in cosmological scenario. So it's a very complex problem. That's why I'm trying to go through the, let's say, road observational, with some idea of chemistry and chemical evolution models, and so hinting where could I use some chemistry to guide me on it. But you have on the top of this old spheroidal a secular bulge, that's for sure.
Okay, thank you.
Regarding the thick disk, you find a 11 gigayear more or less.
Yeah.
Is that do you have an age metallicity relation for the thick disk,
Not
or
really.
is just the average age what you
No,
are
no.
quoting there?
This especially in this paper here, in the Milky Way paper, this is another problem. How you select a thick disk in the Milky Way, right? Here I'm selecting what we call the chemical thick disk. So why is that? When we show the alpha varietal map of the galaxy that we got from APOGEE, you see that the outer parts of the galaxy, even at high distance from the midplane, you have low alpha. So that is not really the thick disk. That is the thin disk going up, right? So what I'm calling genuine thick disk is the old thick disk, the high alpha thick disk, right? And so in the Kepler work, we select the high alpha people, and we see that is very coeval. We even compute this, how coeval is that population we studied there in Milky Way. And it's really like at 11 gigayear it appears. Now there are other ways to compute thin disk, to call thick disk, and people can find a little bit of more spread. But usually it's very confined into that age. So the spread seems to be very small. That's why there are some ideas that maybe the thick disk formed from the impact from Gaia Enceladus, which I'm not totally aligned with for other reasons. But that's why the spread, you're right, the spread on the age of what you call thick disk is something important. We are after that. But to select a good bona fide thick disk is also difficult. That's the complicated. The Milky Way doesn't make our life easy, that's for sure.
Okay, more questions? No? Thank you again, Cristina.
Thank you. Diga-me.
Nós estamos